Okay. Now I guess I'm officially started since it's recording. That there, even though it looks like about half of us aren't here yet, but we won't worry too much about that. There. Okay. What I want to do is kind of carry on where we left off last week. That there, because I feel that this is probably the most important topic for electrical engineering students, is to be able, for an earlier introduction to MATLAB, is not necessarily programming, but be able to analyze complex circuits. Last week I went through and I did a relatively straightforward circuit using DC values, right? I did DC analysis. I want to just, one note needs to, yeah, that's all right. We don't want to, that there. I don't. Hopefully, it doesn't break my computer while I'm talking. So what I want to. This is not looking too promising. What did it do now? This thing wants to keep disconnecting from the projector. Not there. All right, I have it here. I have to have it here since I'm going to be writing. But there. Okay. All right. We have both places. What I want to go to now is looking at AC values and how we would put those in and handle inductors and capacitors using MATLAB, and go through this as, again, using the script format and analyzing this. And it's a little bit more complicated when we're dealing with AC values. And when you took your circuits course, you probably didn't do much beyond a 2x2 with AC values. I'm sure with doing a 3x3 with complex numbers and determinants, it takes you, what, about half an hour to do one problem? That's there. Well, it's going to probably take me about the same amount of time to do the one problem here, because I'm going to explain the process as I go along. Once you see the process, you'll find that it's much easier using MATLAB to do the analysis. And we're no longer limited to a 2x2 or a 3x3. So, any question there, or just... Okay, so I'm just going to jump right in and just teach this by example. I'm just going to do an example of a 2x2, and then we'll move to a 4x4. And I'm just going to draw that there, as with last night's talk, you see me walking in without a handful of notes. That's typically the way I teach anyway. I don't like to have a handful of notes. If I have PowerPoint, sometimes so I don't forget a topic, but this particular topic, I know exactly what I want to cover, so I'm going to skip the PowerPoint and just jump right into the example right there. So the only issue with this example is that it may be completely resistive or it may be completely capacitive, but I'm just going to draw a relatively straightforward circuit here, right here, and we've got an AC source, and I'm going to say that it's, it's an ant, 220 volts right there. And I'm going to give it a phase angle of 0 degrees, right there. And drives me nuts there. And we're going to drive that through a resistive load, a resistor. We're going to put an inductor here. We're going to put a resistor here. And we're going to bring it here. And then we're going to have another resistor here, another inductor, another source here. And we're going to make that also... We'll get crazy, and we're going to say this is 110 volts at a phase angle of 90 degrees right there. So somebody's plugged in an American-style generator into a Malaysian wall socket. Is what we've done here. So we have the circuit here, and we'll just throw random numbers: 100 ohms, 150 ohms. We're going to say 300 millihenries. Right here, 50 ohms, and we'll say 250 millihenries. Again, I'm just making up numbers out there, and what we get coming out of this may or may not be real, exciting to look at out there. But we're going to analyze this circuit, and we're going to do this the same way. We're going to just stick the numbers and up there. Now, I typically just use Z for every value right here. So I'm going to call this, and let me change colors here, and let me lose my glasses since I'm looking at the screen. When I take the glasses off, you all become a blur, but that's all right. Right there. So it's more important at this point that I see the screen. So So I'm going to call this Z1, Z2, Z3, Z4, Z5. I'm going to call this V1, V2 right there. And the other thing that I didn't show is that I need to put a plus symbol there because we have to show polarity on our voltage sources right there. So we're going to just kind of stick this into MATLAB just this way right there. Now, before I do that there, let me just point out that XL, or the impedance that there, or the impedance of an inductor is J 2 pi FL, right? You should this should, you know, everyone's being honest, you've seen this before, right? Sometimes you'll see this written as omega right there. I don't know how they teach it here, but typically, if you know, to be honest, if it was a technology instructor, they probably use 2 pi F. If it was an engineering faculty member, they probably would use omega right there. They're both the same thing right there. So I'm going to just move this over here, and I'm just going to go ahead and bring my MATLAB up. We're going to have to probably shrink this down. View, we'll make it 50%. It's already 50%. We'll make it 25%. There we go. So that we can see the circuit there. Everyone can still see that there. Yep, it's almost readable. Something's wrong. My handwriting's almost legible. We'll fix that later. That there. So we're bringing MATLAB up, and I'm going to just do this in script writing a script. There. And quite honestly, you could do the same thing. I don't know if I mentioned in this class or not. There's another program out there called Octave. That's a free, shareware or open source program. And let's just bring that there. This is a side note. It has nothing to do with that there. It won't be on the project that there, but right there. Here, and hopefully our internet is working in here. There's this program called Octave out there, and it's actually a pretty good program, and it does about 95% of what MATLAB does. And it reads MATLAB M files, and it works pretty much the same. The only difference is it doesn't have some of the toolboxes. So if you wanted to do these problems with your laptops or at home or in the house, dorms, whatever you call it. What do you call it, hostel, or do you call it dormitories? Dorm, okay. You know, I asked in my other class, they call it prison. You know, they refer to it as prison. So, but Octave is a version of, it's a open source program that is MATLAB compatible. It's what I call the poor man's MATLAB. The price is right. It's free, right there. So anything that I cover in this class can be done with Octave, right there. So, and you just do a Google search on download Octave, and you'll see it right there. And you just hit the download button, right there. Somewhere it says the latest is always available from the FTP, right there. And you gotta be careful because it's actually included with Linux. If you install Linux, Octave is included as part of the Linux package, but right there. But it's a shareware version. All right, let's get back to, I don't want the command window. I want to do a new script right there. So let's just bring it on that side here. And I'm just going to go ahead and just start entering the components one by one so that they're in there. Now, I'm going to show the 110 as a, you know, that there, you cannot put into MATLAB very easily or polar notation. And is everyone aware of what I mean by polar versus rectangular? That there. So the 110 has to be put into 0 plus J110 right there. So, you know, so it doesn't handle that very well. So that's the way it handles imaginary numbers out there. So I'm just going to go ahead and put those in. And I'm not going to worry about polarity on the voltage sources at this point. I'm just going to enter the components. So V1 is equal to 220. Z1 is equal to 100. Z2 is equal to, and one of the things I did not specify is, and I'm going to go ahead and specify it, is I'm going to say our frequency is equal to 50. We're going to pretend that we're in Malaysia versus North America out there, which and everyone should be aware that North America uses 60 hertz and most of the rest of the world uses 50 hertz right there. I think Japan might use 60 hertz right there. So, but regardless, let me go back here and let's just put in frequency F is equal to 50. That way I can just include F in there at this point here. So it's going to be 2 times pi times F times, and that's 300 E negative 3 times I right there. So you put the I. It will accept the J as well. You know, mathematicians use I, electrical engineers use J. And the reason we use J is I means something else, current, up there. Z3 is equal to 50. Z4 is equal to 150. Z5 is equal to 2 times pi times F times 250 E negative 3 times I, right there. And B2 is equal to 0 plus, and it's 110 times I, right there. And at this point, I like to just run it to make sure I didn't put any mistakes. And we're going to call this junk 20 or junk 5, I guess, right there. So, and when I run junk 5, it comes back and doesn't do anything because I haven't done any calculations right there. So now what we're going to do here at this point is we're going to go ahead and do our Z matrix. So is everyone clear what I've done so far? All I've done is just stuck the impedances. Did I make any mistakes? Oh, okay. B2 is 110. All right. Okay, there we go. Another reason to use script files is it's easy to fix mistakes instead of doing everything from the beginning. So there we've entered all our components there. Now it's time to just do the Z matrix right there. So Z is our matrix, and for this I tend to like to do the separate lines versus putting the semicolons in between. When we enter the matrix, we can do it two ways. You know, this is going to be a 2 by 2 matrix, and I can do line 1 and put a space between the two components in the first row, and then a semicolon, and then the component or the values of the second row, and then close the bracket. Or I could just hit the carriage return instead of the semicolon. These matrices can get pretty long and drawn out. In this particular case, I prefer to go ahead and put the return. So Z1 has got 3 impedances in it, right? Again, we're following the same rules here. Z1 is in our loop here, and I didn't draw the loop here, but I always draw the loops inside and clockwise, right? So if I draw them inside and clockwise, this is I1, this is I2, and it goes in this direction. So as we look at that there, in loop 1, we've got 3 impedances, Z1 plus Z2 plus Z3. In loop 2, or loop 1 shared with loop 1, you know, I1, we've got 2 impedances. They're opposing each other, right? Because loop 1 thinks the current is going down, and in I2 the current is going up. So we put the negative sign there. parentheses, Z2 plus Z3, right there. So that's our first loop. Our second loop is going to be same thing, minus Z2 plus Z3, right there. And then in loop 3, we've got 4 impedances, 50, and actually we can just say Z3 plus Z2 plus Z4 plus Z5, and close our bracket. Now, I didn't put a semicolon at the end simply because I want to see what the matrix looks like. So I'm just going to go ahead and hit the run. And we go back here. And we see that's... Now, the way this gets a little confusing here, and I'm going to make it full screen right here, is that you'll see this 101e to the plus 2 times. That means it's going to be, each of these values is times 100 right there. So as we look at here, and again, I was afraid of what I was, well, actually, no, I'm in pretty good shape because this is 150 ohms plus J 94 ohms. So it's pretty close to a 45-degree angle that there, not 45, probably more like a 30-degree angle that there. And this is close to like maybe a 20 degree. So these values actually turn out pretty, where we're going to see some that there, because in a few minutes I'm going to bring this up, and I'm actually losing my voice now, so that there. So we'll see how it goes. So there's our currents. Now we're going to go ahead and put our V matrix in here. V is equal to, again, the same thing right there. And I'm going to say that it's going to be V1, and that's going out the positive, so I can just say V1. And it didn't like that there. Oh, I'm in the command window. No wonder it didn't like that there. It's wanting me to enter something here. Let's just do a clear right there, just so that we clear that off, so it doesn't mess. Let me go back to my editor right here, and V is equal to V1, and I can put the semicolon there and minus V2 right there. Right there, and that there, because that's simple enough. I don't need to do that there. So again, I can run this again, and bring up the right window here, and and why did it not do anything there? That's unusual. Oh. Let me close that there. Okay, I should be able to run that. And, well, when all else fails, we save it, we close everything and bring it back. Somehow I broke MATLAB. Not the first time it starts something funny like that. When I cleared, I think it cleared out the script file. Not there, and I have to go back and read. Okay, all right, that brought it back. That sounds a little strange that I would have to close it and bring it back up, but that's what it required me to do. Right there. And as you can guess, that's not the first time it's done that to me. Right there. So again, there's our V, and actually, you know what? I messed this up right there. No one caught that. That should be V right there. That should be V instead of V1 because I changed the value that there, so it's still going to be. It still gives me the same thing there. Okay, so that there again. Our next thing is we're going to look at our currents. Our currents is the same thing. I is equal to the inverse of Z, and I don't know if I mentioned in this class, instead of doing the Z to the -1, I can just use the inverse command. It's a little simpler out there. I deliberately did not do it that way because I wanted to get across what was happening there. And then times V right there, and that should give me my currents right there. So there's my currents. Now, as we look at this right here, we can also go through and we can say, you know, here, and I'm just going to say, here at this point, I'm going to say Z I mag is equal to the ABS of I right there. So that this tells me my currents in terms of magnitude, in terms of how many amps I would expect to get right there. And then I can also say theta is equal to, and this is going to be in radians, so I'm going to multiply it times pi, or 180 over pi in order to convert that there. So it's going to be the arctan of I. No, that's too awkward. I'm not going to bother doing that. But there, I mean, I know how to do it, but it's more than that there. We'll just work with the magnitudes to see that it works. But we can look at the absolute magnitude, the phase angle that there, because we can look at that there and say that it's going to be the imaginary part over the real part, the arctangent right there, and you can calculate that fairly easily. And again, you could do it with MATLAB. I'm just lazy to do it that way right now. I shouldn't say lazy. It's just the command stuff for doing that on an array is kind of that there. So, but if I bring up my calculator Pro, so the first one I'm going to get I guess I got to turn it sideways to get in scientific mode. Here we go. And where's my inverse key on this? Hold a second. So it's going to be, if I look at the first one, I'm going to get a phase angle of 0.7 to 67 divide by 1.35, 1.36 equal plus minus, and the arctangent of that is second right there, and I got about 16.7 degrees there. So, and so when I look at the first one, I got an angle of about 16.6 degrees. That's there. And just remember that there. I'll just put a note back here that I1 is equal to 1.55 and an angle of about 16.6 degrees right there. Because we're going to put this in the MATLAB and we're going to see how that compares. That there. So we can put this in MATLAB multiple ways. If we want to measure the phase angle, we have to do what's called a transient analysis. That there. If we want to just check the magnitude values, we can just put it as a V sign right there. So let's just go ahead and bring up P-Splice, excuse me, right there. In Monday's lecture, I couldn't get this to work because I brought up the wrong version. So let's then go ahead and draw place part, and actually we want to put resistors here. We need 1, 2 resistor, 3 resistor, and then we need to draw place part. We need to get an inductor, and we need 1 inductor. We have 3 inductors, right? I'll have to clean this up here. That's there, and we had another inductor over here. Hmm? Well, let's see, I've got this, oh, there's not one here, right? That one shouldn't be there, not there, okay. So we got this inductor, so there's only two inductors then, right? All right, now we've got a choice here at this point here, as far as sources in PSpice, that we can either put in what's called a V sign for doing transient analysis, or we can do VAC. And VAC is normally used for if we just want to do the quick and dirty like DC, get magnitudes out. I'm going to use the V sign. And the V sign also is important because it allows me to specify phase angles. So I'm going to go ahead and use V sign. Excuse me. And my voice is seriously disappearing quickly. I don't know if you can hear. Can you hear it? Yeah, there. So and I want to do V sign right there. And I have two signs. All right. Let me go ahead and wire this up right here. Right here. I don't know. You're used to using multi-board. I don't know what your thoughts are about your multi-sim of this versus multi-sim. I'm an old timer, so I've gotten used to this, so I prefer the software. My major issue with this software is that it's free. And I also need to do a control P, and I need to do an A ground. I need to stick a ground in. PSpice always requires a ground. And I'm just going to, right there. Now we're going to click this here, and we got multiple values we have to assign for a, there. And this should be very similar to what you have to do with multi-board. But there's no DC offset. We're going to set the AC value to 0, and the reason is because PSpice, when you specify an AC source, it uses AC values if you want to do, like, for example, a frequency sweep. And probably next week we're going to be looking at doing a filter analysis using PSpice or using MATLAB, and then going back and doing the PSpice, where we're going to spend a little bit more time with the logarithmic plots right there. So I'm going to set the AC value to 0 because all we're doing is we're going to do a transient analysis. And transient analysis is very similar to what you would get if you used an oscilloscope. So what we're going to get out of this is going to look very much like a scope display. So I'm going to put this as 0 right there. Now the AV offset we're going to also set as 0 up there. And again, the DC, the offset is, again, if we had an offset like 1 volt or 2 volts DC offset, the DC value, again, is we can do a DC sweep where we can increase our DC value there for analysis. Now our amplitude in this particular case, I'm going to use 220, but 220 is not the right value, right? What is the right value coming out of the wall? Right there. It should be 220 times the square root of 2, right? 220 times 2, where's our square root? That there? I'm not seeing it. There it is. Right there. So you got about 311 volts coming out of the wall. Peak. Right there. Because when you look at, again, I'm assuming this has been covered in your class, but when you look at AC, what comes out of the mains, when you look at the value what that's given, when you see 220 volts, that's the RMS value right there. And in reality, what we're looking at in terms of what we would be seeing in terms of on an oscilloscope, we would be looking at the peak value. Or in this case, 220 volts, it's going to be about 622 volts peak to peak. So we should put in 311 there. Right there. Our frequency is 50. Right there. Save attribute. and our phase is 0 on this one right here. So as you can see, you can specify all the components up there. I know that this is a course on MATLAB and not PSpice, but this is another tool that's worthy of using right there. So that's our first one. Our second one, we go through the same thing. I'm not going to explain each one each time. I'm just going to go through and do it. Save attribute. Save attribute. Amplitude is about 170. That one I know because our frequency is still 50. Right there, save attribute. And the only other thing is our phase is 90. Right there. Save attribute. Alright, let's clean up this display to where it looks right. And this is 100. This is 300 millihenry. Right there. And as I said, it's still taking me half an hour to do a 2x2 simply because I'm explaining every step. But when we do the 4x4, I'll skip a lot of the explanation and just jump right through it. And you can always watch the video if you have questions out there. Because if these videos put you to sleep at night, right? You put them on the computer, you play them, and you doze off out there. So, and redraw. Where's our view? I want to redraw. Yeah, that just cleans it up. Okay, does that look like our original circuit there? Right there. So now what we're going to do here is we want to do our analysis, and we're going to be doing some things set up here. And what we're wanting to do is a transient analysis. Right there. So a transient analysis will bring up another software package called Probe, which allows us to look at this there, right there. Now what comes out of the wall is 50 hertz. So 50 hertz has got a period of what? What is the period of 50 hertz? Right there. Anybody know off the top of their head? I don't know because it's 16.67 milliseconds for out there, so it's probably 20 milliseconds is what I'm going to say it's going to be off the top of my head, but you guys should know that, right? But 50 1 over x, where's my 1 over x on my calculator? And oh, there it is. Oh. Let me clear this thing. I don't know how to use a calculator this morning. Right there. Oh, I'm hitting the second key. That's what's going on here. Yeah, it's easier to just use the Windows calculator. 51 over x. And again, I'm not seeing the 1 over x because it's right in front of me here. They move them. There we go. So it's 20 milliseconds right there. Right there. So it's 20 milliseconds is our period. So as we do our transient analysis, we want to tell it how far we want to do it. Our final time is 20 milliseconds. Let's do about 20 milliseconds. Let's do 100 milliseconds. That's 5 cycles right there. Right there. Close and simulate. And we're going to call this junk. We'll just call it junk 5 to match the other one. Right there. And as it's thinking, and it's showing some values there, but setup. We did tell it transient analysis. Okay, close. Where is our... That's what I'm looking for. It hit it on me. Now at this point, I can now start looking at right here. And let me turn off the displays because those values don't mean anything anyway. So as we look at this circuit right here on this side, and we look at here, what we're wanting to do is let's just look at the current through R1 right there. So we can just hit the plus key right there. Actually, trace, add trace, it's insert key, and we can just look at the current through R1 right there. Right there. And there's our current through R1. And what is its value? Right there. So I don't know, is it similar to what you do in multi-sim? It's similar. Not there. But we can look at that there. Now what we're not seeing here, and this is kind of a tricky thing, is because we used, when we set this up, our values right there as 311 right there instead of, so we're getting the peak current through there, so that's not going to match right there. So if we look at this here, let me just turn on the right here, and we can see, just let's go to the peak. Right there, we're seeing a peak value right there of about, it looks like 2.17 amps right there. So if we took that value, let me remove a couple of things here. Let me unpin that. That way we've got room out there. So if we pull up our calculator again, and we took our 2.18 divide by the square root of 2, we get about 2. That doesn't look right. What did our MATLAB give us? It could be... we got a slightly different value. Our currents should be about 1.55, and we're getting a little bit more than that right there for whatever reason. That number does not look right. Well, actually, no. I made a mistake. I see my mistake. Right there. It's 2.178 divided by clear. 2.18 divided by the square root of 2. There, okay, we get the right value. When I did the divide by before, I think I did 2.87. Yeah, not there. So our piecewise matches. Now, if we want to see the phase shift, that there, which was supposed to be about 16 degrees, what we have to show there is the voltage that there, and it's very difficult with piecewise. What you normally have to do is add a new plot, and you put two plots on the same window. You know, on this plot, we would then say trace add, and we would put the voltage right there. And you can see that there is a phase shift between the two of those, and you could measure that phase shift right there. I'm not going to spend a lot of time doing that. I'm sure in your circuits class that there you learn how to measure phase shifts on an oscilloscope, right? You do it the same way here, right there. You would right there. The only thing is you might want to, when you do the simulation here. Let me redo the simulation here. analysis setup that there is that you might want to print step do, in other words, do something like 0.001 nanosecond. That there to make it very, very smooth. Simulate. Right there. Trace add. And I'm just going to put voltage, the voltage here for right now. The voltage V1, and it's still a little choppy it just doesn't give you a very smooth. Find the exact time of the peak it's easier to find the exact time of the zero crossing, because again you can again you can move this here, and this little window here tells you the value of A1 right there. So, but regardless, I'm not teaching MATLAB. I'm supposed to be teaching, I'm not teaching piecewise. I'm supposed to be teaching MATLAB. So let's get away from the MATLAB discussion a little bit. We'll come back to it though. The only reason I brought the MATLAB or the piecewise up was to verify that we got that the answer is right there. All right, let's go through and let's please start. And I'm not going to go through the piecewise on it. I'm just going to go through the process of a much nastier circuit there, and we will work as long as my page or my voice holds out. It is actually going downhill fast. So I'm just going to draw another circuit here. Actually, what I'm going to do is I'm going to cheat, and I'm going to grab this circuit right here and copy it, because I'm just going to add to it right there. Let's make it a little bit larger right here. And all I'm going to do is I'm just going to stick on it another 220 at an angle of 0. We're going to stick another resistor, another inductor, 50, 100 millihenry, a resistor here, 100 ohms, another inductor, 50 millihenry, and just to keep life interesting, let's stick a 200 microfarad capacitor in there, just so we can stick a capacitor in there. And the only reason I did this is just to make our life a little simpler. That there is now we've just added some things to it. That there, and I'm just so I can leave in my M file what I have already. That's why I added to the circuit, just simply to make our life a little easier. So we're just going to call this V3. This one we ended with Z5, right? So Z6, Z7, Z8, Z9, and Z10, right? So we're just going to add to this, and I'll go through this up there, and at that point I'm probably going to be at the point that I'm going to have to say my voice is. Now my voice was fine before I started this here, so I don't know. So I'm going to delete this right here, right there, because we're just adding to the circuit right there. So let's just go ahead and put the caps lock on, and we're going to say V3 is equal to, and it looks like I'm going to have to, let's view. Let's say 22%. I'm just trying to get it all on the screen there. V3 is equal to 220, right? Z6, is that right? Is equal to 50. Z7 is equal to 2 times pi times 100 e negative 3 times I, and it's not going to like that. That I has got to be lowercase right there. See, the uppercase I it rejects. It has to be lowercase I. And actually, I think it's going to reject the pi as well. Right there. Okay. Say again? It's still there, 50. Yeah, everything's got, yeah, let's keep our life simple. One frequency. That's there. Okay. That's there. Okay, thank you. You know, I'm so fighting my voice trying to go bad that I'm not thinking clearly, and which is going to happen. This is not Monday morning. I should be doing these things. Z9 is equal to 2 times pi times the frequency this time. Times 50 e negative 3 times I. Right there. And Z10 is equal to 1 over 2 times pi times the frequency times 200 e negative 6 times I. Now I put the I underneath there. That will bring it out. As a matter of fact, let me just take the semicolon out so that you can see that it will show it as a negative I right there. Because 1 over I is negative I by definition up there. So that's everything there, right? So loop 1 and loop 2 stay. My loops all change now. So as we look at my loops right here, right there, let's red. There's our third loop, I3. Here's my fourth loop, I4. So we're just going to go ahead and we're going to start sticking our loops, do our Z matrix. Z is equal to, loop 1 is going to be the same. It's going to be Z1, and I'm going to hit the caps lock here, Z1 plus Z2 plus Z3. The next one is going to be minus Z2 plus Z3. That's the same. Now loop 3, now I've got minus Z1 there, right? Right here. Loop 3 and loop 1 has this shared component, minus Z1, and 0 for the next one. Because between loop 1 and loop 4, there's nothing there. So we go ahead and do our next loop, minus Z2 plus Z3, right there. In loop 2, we've got 50 plus, and what am I doing? 50 here. It should be Z3 plus Z2, right? Plus Z5 plus, and that's it, right? Plus Z4. Plus Z4. I almost forgot the Z4 hanging here. That's an ugly circuit, isn't it? Be honest, isn't that an ugly drawn circuit? If you're a CAD operator and you drew that, your boss would probably fire you, right? Up there. But for up there, between loop 3 or 2 and 3, there's nothing, right? And between 3 and 4, or loop 2 and 4, there's Z4, right? And they're in opposite, minus Z4, right? So now we're going to go to loop 3. Between loop 3 and loop 1, there's minus Z1. And between 1 or 3 and 2, there's 0, right? In loop 3, we've got Z1 plus Z6 plus Z7 plus Z8. Right there. Is that all of them in that loop there? Z1, Z6, 7, and 8. Right there. Between loops 3 and 2, there's nothing shared. And here we've got minus Z8. Minus Z8. Right there. Now we're to loop 4. Loop 4 and loop 1 has got nothing. Between 4 and 2, we've got minus Z4. Between 2 and 3, we've got minus Z8. Right there. And then we've got Z8 plus Z9 plus Z10. Right there. I'm going to run this, and the reason I want to run this is I want to make sure it's symmetrical. That's a test to see whether it's right. Right there. And we have a problem. Unbalanced or expected parentheses or brackets. So somewhere I got a bracket that's misplaced here. This is line 18, right? Line 18, column 25. So it's line 18. So it's this line here. Right here is where it's at. Okay. You saw it. I couldn't see it that there. Well, that there. So let's go ahead and run this again. And dimensions are being contended. All right, it's got an issue somewhere here. This is telling me that dimensions are not consistent. That we've got something. That's why 1, 2, 3, 4 components. 1, 2, 3, 4 components. 1, 2, 3, 4. Oh, we got an extra one here. Right here. All right. That's telling me this is the third loop. The third loop should not have anything with Z1 minus Z1. That 0 is right. This is right. This 0 shouldn't be here. Right there. So, and you can see why I do this, because it's easy to make these mistakes. Right there, we found 2 of them right there. Okay, now we're looking at this right here. So what we're wanting to see is if this row here matches this column. So 1.5, that's that there. These 2 should match. They do. These 2 should match. They do. These 2 should match. They do. This one should match. This one. Excuse me. This one here should be its own. This one should match. That's the 4th one. Should match this one here. Right there. And that looks about right. Let me just do an A. Sometimes it's easier just to do an ABS. Z. That there. Because you look at the absolute values and that's close enough. Instead of trying. Am I in your way there? Can you see? In other words, this row here has to match this column, which it does. This row here has to match this column, which it does. So this is a symmetrical matrix right there. So it is symmetrical. So I have to assume at this point we've got our Z's right. Right there. So now let's go back here. Let's stick in our B's, which is much easier. B is equal to bracket B1 and B2. Second loop we got minus minus V2. The third one we've got V3. I didn't show the plus sign, but we're going to assume the plus sign to be here, okay? I left the plus sign out there. And then the last one, we have 0 right there. And we would then say I is equal to inverse B times, or excuse me, C times I, or times V. Yep, that's right, yep. If we run this right there, we have our, there's our currents. Now I'm not going to go through and go through and do this in piece-splice to verify, but that's our currents right there. This is how we would analyze a 4x4. It took a little bit longer than the 2x2, but again, I cheated by using the first half of that there. But I guarantee if you were to do this without MATLAB, you're talking hours, literally hours. Because did anyone tell you how you do a 4x4 matrix on determinants? You solve 4 3x3s. Is the way that you do it. You have to expand it out right there. So it's a very difficult process right there. So, all right, I'm going to wind out at this point there. Let me do the attendance before I get in trouble with that there. And let me also, while that's coming up there, I don't want to. I'm going to try to post the final project on e-learning first, but if you don't see anything by Sunday, you might want to just give me a WhatsApp message and ask me to send it to you. That's there. My phone number is 017-211-2207. Don't give me phone calls because I'll ignore phone calls. I'm good at ignoring phone calls. So that's there. But just send me a WhatsApp that there, and what I'll probably be doing in the future is I'll probably set up a WhatsApp group for most of my classes. That way it's easier. That or a Facebook page. Facebook page might be easier to maintain and less work from my viewpoint. That there. Because the problem with a WhatsApp group is that you send a message, everybody in the class gets the same message. That there. And they would get quite busy. That there. So I'm looking at doing a Facebook page only because of the problems with that there. With Facebook, I can post links to videos. That there. So, all right. With that said, let me go ahead and wind this down. Right there. I still talked an hour.